All right. Is this stream working? It looks like it is. Let's make sure my phone agrees. Am I going to hear myself? Is there like this long of a delay? Oh, there we go. All right, there we go. All right, everyone, welcome to my office hours for this week. Someone in chat says poning time. Yep, it's time to pwn some challenges. Take a look at I guess whatever everyone is interested in. So, are there any questions to start us off with for this office hours? All right, I see someone interested in discussing 9 and also discussing 11. Okay, let's see here. And also 11 and 12. All right, we'll take a look at 9 first, since that is an earlier level. All right. Do you have any specific questions on 9? Okay. All right, so I'm waiting to see what the specific quote, there it is. Okay, I guess the general concept of how to write to memory to jump the canary. All right, is this like lagging? It's lagging. Hopefully it doesn't lag for too long. All right, let's see here. What does this level say? Okay. Buffer is whatever bytes long. Arbitrary length. There's no win variable. It's only the first couple. We have a win oft function. Okay. So there's canaries enabled. This program reads your input 1 byte at a time, tracking how many bytes have been read and the offset from your input buffer to read the byte to using a local variable on the stack. So this is approximately what it looks like. Well, this got formatted wrong. Interesting. Okay, so it says something like while n is less than size. So I guess we get to specify our size, I suppose. Yeah, because if we look down, we get to enter our size. So while n is less than size, we read from standard in, and where we're going to read to is input plus n. So n is probably how many bytes we've already read. It's probably initialized to 0. And we're just going to read a single byte. So I think the idea here is that if for whatever reason a syscall decides that like, hey, I want, or let me re-clarify that. So in general, while programming, if you want to take in exactly 100 bytes and you do a read syscall and ask for 100 bytes, and the user initially only inputs, say, 20 bytes, you might, in the course of creating your program, want to repeatedly call read until you've read all 100 bytes. So this logic looks basically how you would accomplish that. You read, you increment n, how many bytes you've read, and then you read to the input plus how many bytes you've already read, and you just keep reading. So this would be a way to accomplish that. It's a little inefficient because we're reading a single byte at a time, but this is certainly one way to accomplish that task. Okay. Anyways, as it turns out, you can use this local variable n to jump over the canary. So yeah, as we've learned in the previous levels, the goal is to overwrite the saved instruction pointer with basically where we want to start executing. The issue here is that there's a canary in the way. So if we just read in, say, 200 bytes and smash through the stack, we're going to overwrite the canary and we're not going to successfully execute our function because we're going to stack smashing detected. Okay. But it tells us very nicely that when you overwrite n, you will change the program's understanding of how many bytes it has read in so far. And when it runs read 0 input plus n1, again, it will read into an offset that you control. So the idea would be that if we can, as part of doing this, this read in, if n is a variable on the stack that appears before the canary, and we can overwrite n while still keeping n less than size, we can basically specify an n value that is past the canary. And if it's past the canary, now we can continue basically reading in input without ever clobbering in that canary. So say the canary is at, does it tell us? Somewhere it would tell us. Say the canary is at offset 100 and n is at offset 80. If we pass in to basically read in, say, 1,000 bytes, and we start by reading in 80 A's, and then we overwrite n, which is on the stack, to point it now at, say, 110, which let's just pretend that's where the saved instruction pointer is. Now it will continue reading into input plus 110, and we'll have written to input through input plus 80, and then we'll start reading into input plus 110. So we would have never clobbered the canary there. It's kind of what it's talking about. Okay. The payload size is deceptively simple. You don't have to think about how many bytes you will end up skipping. True, we just need to make size sufficiently large, because if it's sufficiently large, as long as n can stay under size, we're good to go. So we can just do like 1,000, we should be good. You don't have to think about how many bytes you'll end up skipping. Okay. Yeah, there's no difference between bytes skipped by fiddling with n and bytes read in normally. Yep. You do need to be careful on the sending side. Don't send the bytes that you're effectively skipping. Right, okay. So someone's asking, I guess, the general concept of how to write to memory to jump the canary. So the most important thing that we need to think about in order to skip this canary is what is the offset from the start of our buffer to where n is stored. And then I guess what is the offset from the start of our input buffer to where the thing we want to overwrite, which is the saved instruction pointer, is, where that is. So let's just start by specifying a random payload size of 200. We'll send it ABC. Oh, I guess maybe we didn't want to do 200 because it's going to completely read until we get our 200. Let's restart that. Let's just send it 3 and we'll do AB new line. Okay. So we can see here that this is the status of our stack. So I'm basically just doing this so we can use the teaching mode to get all of our offsets. If you're specifically interested in how we could do that in GDB, I can show that as well. But for now, we're just going to use the teaching output to determine this. Actually, maybe we will need to use GDB. I'm not sure if it's telling us where n is located. Maybe it is. The address of the number of bytes read counter and read offset is this. I guess, yeah, and basically the address of n is right here. Okay, so the thing we care about then is how far away is this value from the start of our input. Oops. But can I use Control-Shift-C? Maybe. Looks like it. Okay. Yeah, GDB would be great if it's not too much of a hassle. Okay, so we'll look at how you would accomplish this as well in GDB after. We'll start with the teaching mode basically, and then we'll look at how we can basically recreate this in GDB. Okay, so we know that n is 104 bytes away. So if we write 104 A's, the next bytes we start writing are going to be overwriting n. Hopefully that makes sense. And then the canary value is now, actually we don't care about that because we're just going to skip it. We're just going to go straight to the saved return address. Okay, so we want to know where that is. So we want to know this. Did I copy that correctly? 7FD. Oh yeah, okay. Where this is minus this. Okay, so at 104 bytes in is where n is, and we don't necessarily know the size. N might be an 8-byte value, a 4-byte value, a 1-byte value. It's not super clear, but fortunately because it's little endian, it doesn't really matter. At least, yeah, in our case, it doesn't matter. So currently, n is going to start out at like 0, or it's going to start at something less than what would take 1 byte of space to store. So the remaining bytes of whatever the data size is will be zeros. So whether it's as I said, whether it's a 1-byte value or an 8-byte value doesn't matter because of that little endian storage, which is kind of why programs tend to store things in little endian. It's easy to convert between sizes. Okay, so we want to send 104 A's, and then we want to send 136 represented as a little endian integer. And then the next bytes that we start reading in are going to be writing to offset 136. So let's look at that. If we do import pwn, do we want to just do it? Yeah, whatever. We'll just do it in IPython. If we do import pwn and then pwn context, this is so annoying though. It's like laggy-ish in the terminal, I've noticed. So we'll just type it over here. Okay, so we want to do target send after, or I guess I like right after. They're aliases, but whatever. So basically, after it asks us for a size, so at some point it asks us for this payload size. So after it asks us for a payload size, we want to send it a payload size. And this doesn't really matter. It just needs to be sufficiently large. Is that true? We would have to fill out the remaining bytes if we do end up making it 1,000. So maybe we should just make it correct. I think we're interested in 137-ish, or let's see here. The address of winauth is, we'll just do 137 for now so we can demonstrate what we're doing. And then we want to write 136 A's. Oh, and we need a new line here because when it's asking us for these numbers, it's using scanf, and scanf is going to be white space delimited. So we need to make sure we have a white space character, such as a new line, after we send our size. And then we just want to write 136 A's. So that is going to go, that's not exactly true. We want to write 104 A's because 104 is how far we have to go until we are looking at n. So this now means the next value we write is going to be clobbering n. So now if we do some value, and what value we want to do is we can use, here, let's look at it in IPython real quick. What we want to write is, if we do import pwn, basically we need to encode this 136 correctly as a little endian integer. So if we just do pwn.p8 136, that gives us our correct packing of it. Basically, we couldn't just say like 136, right? Because that would take up 3 bytes of ASCII. We're not sending an ASCII value. We're overwriting that actual memory that's there. So if we want to pack it in the same way that it's actually stored there, we can use this p8 function. Alternatively, we could just do like bytes 136 in this case because it's less than 256, and that'll give us the same thing, but let's just go with p8. So pwn.p8 136. So we just overwrote n now. So now on the next read through, so you think of this, right, we're in this tight loop and it's constantly going off of this n value. so in this right here, we are overwriting n. So that means on the next one, when it goes in to start reading to a new offset, it's going to be using this value, skipping over the canary. So now what we want to write is, we'll just write an, I don't know, an A. And that's basically going to be overwriting the last byte, or the least significant byte of our return address, which we'll see. So now if we do target dot read all, and we'll set this to debug, we will see what we're talking about. So Python x.py. Okay. So we can see, did we mess up? Previously to main, yeah, we must have messed something up. So that A would have gone somewhere. Question is where? Let's see here. How to debug this? Oh, I guess it's telling us how far it's going. This is 104 bytes away. Was 104 correct? What did our calculation before say? It said 104. Let's see here. So we overwrite here. And then I think we're off by 1 if I had to guess right now. Slightly surprised by that. So, I mean, we can look at this directly, right? So it says about to read 1 byte to this offset. So this offset must be what n is, and we're incorrectly sending it an A. So C98. If we look at this, this is C98. Yeah, so we're sending it, we have a off by 1 here. We're sending an A to be the new value, and A is going to be hex 61, which means n is going to get set back to, you can see this. So basically we're sending it an A instead of our 136 encoded. And if we look at the ord of A, it's a 97. I'm not entirely sure why it would behave this way, though. Either way, let's try, before we think too hard about it, let's just try fixing our off by 1. So I think what we want is this to be 103. Yeah. We're still off. 36. How are we messing this up? So this is 104 bytes away, and now so now it's saying 98, which is kind of what I expected for our off by 1 before. Because that 98 corresponds with our A, right? 98. Where are we off by 1? So we send 103 A's. But that can't be right. I think, are we off by 1 here? Does this need to be 138 and then we go back to 104? And let's see here. Yeah, that looks correct. It's not immediately obvious. It's clear that there is an off by 1 going on here, but it's not immediately obvious why that's the problem. Okay, about to read 1 byte to, so we were about to go to 104. This must be where we correctly send in our 136. And then we're going to 137. So are we off overwriting the second to last value now of the win address? Saved win address. No. About to read 1 byte. Why are we not seeing that? Where is that A going? So we're about to write to somewhere there's going to be another 61 here. This right here is our 61. I think the 136 should be 135. Oh, you might be right there also. I agree, because something, in the same way that we had an off by 1 here, I think we also had an off by 1 here. Because we can see a 61 ending up here. 5, 6. Oh yeah, the 61 is here. The saved return address is now pointing to, kind of surprising this doesn't crash. Or maybe it is. Print targets dot poll true. I guess we'll do pwn.info. Don't know why it's not showing me the exit code here. Stir. Okay, we are crashing. So we're segfaulting here. So this needs to go down to 135. So I think the issue, why do we have an off by 1? Where is that description of the loop? This. Input plus n. Read is 0, input plus n. N plus equals. So I think this plus equals is causing our off by 1. So read, so if you think about it this way, right? Read is going to read in 2 input plus n. And in doing this right here, at this point when we're trying to overwrite n, so we want n to become 136, right? We have to send it 135 because we're going to clobber it with 135 as a result of this. So now n is 135, but it's going to add 1 because read just read in 1 byte. So it's going to do that 135 in the clobber, and then it's going to add 1 because it read in 1 byte. So that's what's causing this off by 1, I believe. Yeah, that is my understanding here. Okay, so now we can see, if we look at, we have to run it again, I think. 35. Yeah, and then I think this right here now can go back to 137 as we initially thought. So basically 136 to get up to the saved instruction pointer as we calculated before, and then 1 more byte just to overwrite a single byte to show that we can't overwrite a single byte. And now if we look at it, yeah, because before it was hanging when we had it on 138 because it was looking for an additional byte. We'd have 138 if we wanted to overwrite 2 bytes. So now we can see the saved return address is now pointing at this thing that ends with 61. So for instance, now if we do 138 and we send, say, 2A's to overwrite 2 bytes of that address, we can see now it is 6161. And hopefully it's clear on how you would now take this to an actual win. Okay, so someone was asking, I think, about how we would determine where n is. So let's just quickly look at just the testing real quick in GDB, and then we'll look at another level to see how you would determine the address of the number of bytes read counter and read offset is this. Because once we have this, basically all we needed was this, this, and this. So if we look real quick at the testing version, just to show how we would compute that with GDB, because I think it's very important to be able to do this in GDB, right? Most programs you're exploiting aren't going to tell you the layout of their stack and where everything you care about is. So you need to actually be able to compute these yourself. So if we go to workspace, and if we do GDB challenge this blah start, how will I want to show this? We can just show main real quick. Disassemble. Oh, we need to set disassembly flavor Intel. Wonder why it's so laggy. It's very sad. Okay, so disassess main. So somewhere it's going to be calling our we need disassess challenge. So somewhere it's going to call read. It looks like it's calling read right here. And it's going to be using basically all of this logic right here that's setting up the arguments to read is going to tell us basically everything we care about. So if we analyze this, we see it's using RBP minus hex 48. Moving that into RAX. It's pulling that out. Okay, so this is slightly more complicated. We have to figure out where RBP, who's writing to RBP minus hex 48. I guess what we can do actually is just, how do we want to do this? No, we need to keep looking at this. And then we pull from RBP minus hex 50. And we're going to, so we can see that this is a pointer. This value here is actually a pointer because it gets dereferenced again. Whereas this one does not seem to be a pointer because it doesn't get dereferenced again. We just add. So we can think of it, right, at some point in doing this read, we know that EDX is going to be 1 because that's the third argument and it's reading in 1 byte. EDI or RDI is going to be 0 because it's reading from standard in. The confusing one, or I guess the important one, is RSI. Where is the buffer that it's reading to? So however RSI is computed is the thing that matters. So RSI comes from RAX. RAX comes from adding RAX with RDX. So now we care about RAX and RDX. So we care about this, and we care about this. And which means we care about this and this. So we can see this seems to be where N is stored right here, RBP minus hex 50, because that's getting added. And then this is a pointer that contains where the buffer's pointer is, basically. So if we just break here real quick. And we continue, it's going to ask us for a size. We can just say 200. And we can see right here. And maybe what we want to do is display 8i RIP. Okay, so we're about to take RBP minus hex 48. So if we look at x, gx, RBP minus 0x48, we can see that this is a pointer, which also points to the stack. And then if we dereference that thing, though, and I wonder if I can do, let's just copy it. If we dereference this, this is probably where it is. So this is going to be, I think, where our buffer is. Maybe not. Hold on, let's step through this. So, okay, if we, let's just also display GX RAX, so we can just keep track of RAX at all times. Wait, we want to print RAX. xgx, it's good enough. I think we'll just have to deal with it, dereferencing it, but we can see the value over here. Okay, so if we step, we can see that RAX now contains this value. We're going to dereference it, right? We're dereferencing RAX. We're going to get this value, which is now just 0, apparently, because we moved into EAX. We didn't care about those higher order bytes. So maybe this is our n, actually. And let's see if we continue stepping. We're going to, so we just move this into RDX. We're saving it in RDX. If we step again, we're going to see that we have this address. So this might be where our buffer is. So yeah, I think this is our buffer. We're going to add them together. We're just adding 0 to this. So it's going to be the same value. And then we're going to go through with the read. So if we continue and we send, let's say, our A, and now we're basically in a loop. We're back to where we started. Now we should see that after we step through these two values, that our n is, can I step? I don't know why it's not giving me a prompt. We should see that this value now is 1 when we get to here. So if we step, okay, we're about to dereference it again, so we can see this now contains this 8 thing. Oh, maybe I might have messed something up where we went through twice because we sent an A and a new line. But now n is 2, we can see here. And what we care about, or this other value, which is the start of the buffer, probably isn't changed. Yeah, it looks like it's the same. And then we're going to go through and add them together, so now we're 2 further along. So we can see then that we disassess challenge. Basically, the values we care about are this right here contains a pointer to n. Okay, let's go through one more time. I want to see the values live. So if I continue again, I'll just send an A. And I don't know why it's not letting me hit my breakpoint. Don't know what's going on there. We step. So this contains where n is. So if we overwrite this right here, we are going to be overwriting n. So it's showing it as REX. Really, we're just using EX, which we can see with this move. So these higher order bytes don't matter. So we need to overwrite basically at this offset. And where is this offset relative to this? So if we do px rbx minus 0x50, because we said that this is where our buffer is. So if we look at this, and we do why does this look weird? Does it look weird? Okay. Like, what is this minus this? Oh, maybe it's not weird. We need to do the other way around just so we don't get this stupid sign stuff. It's a negative number. Okay, I guess it's not weird. So this is where n is stored, which we looked at by analyzing this program. And this is where the buffer starts. So 56 later, basically, is how we get to n. Does that make sense? Hopefully that makes sense. So this is where we figured out by kind of like looking at the logic, kind of stepping through it, understanding what the program's doing. We've determined that this is where n is. We've determined that this is where the start of the buffer is. So if we write 56a is the next value we write is going to be overwriting n. And then similarly, so actually we can just to confirm it, we will get ready to show that. So 56. And then the other thing we care about is where is RB or RBP, and then 8 higher. So basically, where is RBP plus 8? Because RBP plus 8 is going to be where our saved instruction pointer is. RBP contains the saved base pointer. RBP plus 8 contains the saved instruction pointer. So if we do P/D RBP plus 8 minus this, and that RBP and RBP plus 8 stuff is just, that's how the stack always ends up looking. So we know that this is where the saved instruction pointer just always is. This is where the start of our input buffer is, so at 88. So if we want to do, let's say 90 to overwrite 2 bytes of it, we want this to be 88 minus 1 because it's going to add 1. If we run our script now, hopefully we will see, well, I guess we'd see a seg fault. What just, oh, that was weird. So we sent 90. We send our 56As. Send that, send that. We off by 1. Is it closing because, why are we off by 1 again? Let's see here. So we were thinking RBP plus 8, which is where the saved instruction pointer is, minus this, which seems to be the start of our buffer, gives us 88 bytes away. This is 56. P8. Why is this failing? This is so sad. The fun of doing these challenges. Okay, here's the easiest way to figure this out. So let's go back to our old solution real quick. And then let's go back to the teaching mode. Let's look at it in GDB with our teaching output available to confirm that we're doing it right. That's going to be the easiest way. I mean, otherwise we could just walk through it in GDB in the testing variant, but it'll be easier to walk through in GDB in the teaching variant because we know what the correct value should be. So let's do GDB challenge this, disassess. Why are you lagging? Maybe I should start doing this in the terminal. Disassess, oh my god. Disassess challenge. Forgot to do set disassembly flavor Intel. Wow, this is really lagging. Disassess challenge. Okay, where is this read call happening? We're gonna have more stuff involved, but that's fine. Somewhere we're going to see a read. Right here. Okay. So this is where we want to break. Did we not start? That's so sad. But we can use this offset. Break challenge plus that. Oops. We will start. We will continue. We'll give it a random payload size. We will display 8i RIP, display GX RAX, and we will start stepping. Okay. So this gives us this address, which seems to be the address that contains n. And then step. Now it's 0 because the first time through it'll be 0. Do the sign extended move thing, doesn't really matter for us. And then we're going to take RBP minus 90, which seems to be where our input buffer is. So we're thinking that this should be this minus is it this value? Yeah. Of course, we did it backwards. So that is 68, 104. So this is our 104As as we computed. And I guess the only other thing that we were interested in was the instruction pointer. So this is our 104, which we correctly computed. And then the other thing we were interested in was RBP. Hold on, am I changing the value? 68800. Yeah, this is our input buffer. RBP plus 8 minus that. That. 136. Okay. So all of our logic of doing GDB looks correct, which we've confirmed now with teaching. So there's our 104. This is our 136 minus 1, which we'll just show real quick. And okay, when we send two A's, we saw that when we run it, Python x.py, segfaulting, but we're overwriting two A's. Save return address is now pointing there. Yep. Okay, and then let's go quickly back into testing mode. Challenges. Workspace. And oh, this would be so much easier if it wasn't lagging. I probably should start doing my office hours in SSH and or figure out how to get rid of this lag, but that might be much trickier. This is x/8i or no, challenge. And I also, let's go ahead and fix this real quick. New file, GDB init, set disassembly flavor, Intel. No more making that mistake. Okay. Disassess challenge. Looking for our read. Here's our read. We're looking for before the read. Right here. Plus 180. Break challenge plus 180. Start. Continue. 100. Display 8i RIP. Display GX RAX. Step. And then step. So this is where n is. And then step, step. This is our input buffer. And then this is where n is, which should be further. If I didn't just do this wrong again. Let's see. Nope. Okay. So that's 40. Was that 40 before? I don't remember what I put, but let's just say 40. Okay, then the other thing we care about is RBP plus 8. Realistically, I should have done a GDB script for this so that we would be doing the exact same calculations between teaching and testing and not theoretically making a mistake here. But whatever, we're committed now. So this needs to be 74. We want this to be 72. Okay. And Python x.py. Okay, I don't know what I did wrong before, but that is how you could compute them in GDB. That was definitely long-winded. But that is just how this goes, you know. It's a very fun process when you make mistakes, and making mistakes is how you improve. Okay, so that covers that, hopefully. And in fact, we could, just to really show it, we should have a core dump here now. Is it creating core dumps? Oh, I guess that's an interesting thing to show off. If we do no suid, no set UID equals false here, when we create this process, that's going to allow pwn.tools to make this no longer be a suid process. I'm not exactly sure what's doing under the hood. It might be copying the binary. There might be some syscall you can do on a personality thing to make suid no longer happen. Not really sure. But either way, it disables suid. Now, if we ls, we can see that we have this new core dump thing that was just created. And this core dump thing lets us know basically where we're crashing. So we do now GDB challenge this, and then we do core. We can see that we crashed here with 6161 being in our address. In fact, we can also do is we can do pwn.core dump. We just do core. Maybe we can do core. Let's try it. Core. Say that this is our core dump. Or maybe we'll just say this is our core. And does that work? No, I guess we need core dump. Core dump. Okay, so we can see that pwn.tools can actually parse these core dumps, and we could use that to immediately just tell us basically what the saved instruction pointer is when we crashed. And so we can do like pwn.info core dump dot. I think you can just do RIP. We may have to do like registers.rip. Saw that show up real quick. This in a string. I guess we want hex. What? This just isn't hex at all. I'm so confused. Why is it not printing hex? Did it not save? Maybe it didn't save. Let's try again. Oh, there it goes. Okay, yeah, so we can see that we have this 6161 in there. So yeah, that is how you can use core dumps in pwn.tools, which I guess is not super useful here. But if you wanted to start brute forcing stuff to determine offsets, which might be useful in other challenges to just kind of like automatically figure out these offsets. It's a little trickier here because we're like jumping stuff. But in some of the other challenges, you could like repeatedly brute force an address and then you could basically grab out where it crashes. So you could use that cyclic pattern stuff, figure out where it crashes and then pull out where it crashed here. That's how you could start automating stuff. Yeah. Okay, so what did we want to look at next? Okay, so there's also people asking about 11. I've seen 11, 12, 11 or 12. Okay, let's look at 11. Is there a specific question that anyone has about level 11? What is this doing? We have later levels that use mmap. Oh, this is like a challenge that goes in a different direction, isn't it? This challenge stores your input buffer in an m-mapped page of memory. Okay, so we can see we call mmap, it gives us this. The flag is going to be loaded into memory. It's never going to print it to us. Print the buffer storing the flag. And then it's going to do, I guess, some more. Okay, so this is where it maps flags. Flag ends up here. Call mmap a couple more times, just kind of add some padding or whatever. Then it does this. Okay, so maybe we just say 100. You've chosen to send 100 bytes. This will go here. It's going to be 14 bytes beyond the end of the buffer. We'll say ABC. Okay, so and then it tells us what we said. So the thing to note is that unlike a lot of higher order functions inside of the standard library for C, which start null terminating strings, when it's receiving our input here, so for instance, this uses scanf and it's taking in 100. I guess in this case, it's going to convert it to an integer, so that's not super interesting. But for instance, if you used the function gets, which is going to try and read in a string until you get to like a new line character, I believe, it's going to turn that new line character into a null byte. So it's going to make sure that strings are, in C, strings are null byte terminated. But that's not how it works for the read syscall. The read syscall doesn't do any sort of null byte termination because that doesn't make any sense. You might read in null bytes, so there's no concept of null byte termination. You have to keep track of lengths. So what that means for us is that we have this thing saying you said, and it's outputting to us what we said. So I guess we do objdump -d mintel challenge this less, and we go to challenge, and somewhere near the end, it's calling, it's probably going to do print. Let's see, how is it doing this? You said. But doesn't read a string, or does it not matter? So when it says send your payload, I guess what's the way to show this? 3db challenge baby mem, we'll do start, we'll do continue. So asks us for a size. In fact, if we hit Control C here, we can see that we're in a read syscall because ultimately it needs to use it. But if we look through the backtrace, we're in a scanf right now. So that is how it's reading in this size here. But if we continue, is it still asking for that? Let's see what happens. 100. Okay, yeah. If we hit Control C here now, we can see we're still in this this libc wrapper for the read syscall. But we're not in like scanf or a higher order function. We're like basically just directly doing a read syscall. This is not going to add null bytes anywhere unless we send it null bytes. So that's important. If we continue, I think it's like test, and then it says you said. So when it's doing this you said, it's doing string stuff. So I guess here's how we can show that. Somewhere basically what we would do to show this, you could reverse engineer this program and see what's producing this you said. It's going to be like a puts or a printf or something. It's probably a printf. And I guess in fact we could probably quickly see that if we do this and grep for you said. Yeah, so we can see it's doing a format string, so it's probably passing this off to printf. So for instance, if we do challenge baby mem blah blah blah, and we do echo 100 new line test, and then like null byte it. You can see what's going to happen here. We need to get that to be correctly interpreted. We can see that the it just suddenly vanishes, right? Because it's looking for a null byte character to determine when the string is done. And if it's not there, it'll just keep going and going and going because it's just a %s. So it's not even like a %.20s or whatever to say like, hey, we can be 20 characters long max. It's just a %s. So it's just going to keep outputting data until it gets to a null byte. So if we send it a very large value to get at the difference between here, the address of the flag is here, and our input buffer is here, so if we send hex 3000 A's and no null byte, suddenly the flag is going to be part of our string. Hopefully that makes sense. If you still have any questions about that, let me know. We can go over it more. But yeah, that is kind of the idea of this level. And I guess it's also important to note that these M-maps are going to kind of happen deterministically. Even though the base address of these M-maps is randomized, the offsets between them is going to always be constant. It's you could run this multiple times and you'll see that these are always hex 3000 apart. This leading part changes around, but the offsets don't. Okay, so that is all I'll say about level 11. And then what else are people interested in? 11 or 12? So I've seen some people are curious about 12. Let's quickly look at 12. We run the program. Before we do, okay. Input buffer. Program will let you provide an arbitrarily large input length. No win variable. Okay, this is probably the important bit of info. Because the binary is position independent, you cannot know exactly where the win-auth function is located. This means it is not clear what should be written into the return address. Okay. So if we say 100, let's send test, you can see what it's talking about a bit more. Address of win-auth. Okay, so there's also a canary. Oh, I guess there's more data. Okay, overwriting the entire return address is fine when we know the whole address, but here we really only know the last 3 nibbles, because these last 3 nibbles aren't affected by ASLR. Those are just, if you think about it, a page is size hex 1000, and ASLR works on a page granularity, so it's randomizing basically the base address for where these pages are going to be. And if we talk about nibbles, nibble is just basically half of a byte. It's 4 bits. It's 1 hex character. So if we think about, this would be 2 bytes, right? This hex 1000. This is a byte. This is a byte. Each of these is a nibble. 4 bits, half of, or 1 hex character, 4 bits, half a byte. So we can see here that if it's a page granularity, basically everything from this 1 and up in the address, so we can imagine that the address could go further. Maybe it's going to be like 7F, whatever. Everything up here is part of that page granularity, because this is where pages would be, but this is going to be contained into a page, and this is 3 nibbles because we can see it's hex 1000. These are 3 nibbles right here. Those aren't affected by ASLR, so we know them. It's just going to be the, yeah, hopefully that makes sense. And I guess it tells us that. These nibbles never change because pages are aligned to hex 1000. This gives us a workaround. We can overwrite the least significant byte. So you can imagine that, I guess we don't even have to imagine, we can see exactly what it's going to say. So the current saved return address is here. And the address of when auth is here. So let's just pretend that we want to jump to the start. Obviously, we know from past levels, we can't just jump to the start. We need to jump a little bit further in. But let's ignore that for now. So this is that granularity we were talking about. So these 3 right here, we know. So we can see that all of these bytes, they don't matter. Because if we can just, so for instance, I guess, yeah, we'll show here. If we can just overwrite the last 2 bytes right here, how do I want to say this? Let's pretend here that the win function is right here. This will make it a little bit easier. So we only need to overwrite, let's say, the last byte. Well, if we just change this D3, which is what it currently is, into a 1-3, we will have successfully changed the saved instruction pointer to be the win function. And we don't even care about these other bytes. They just don't matter at all because they're already correct. All we had to do was change this last byte. We don't care about ASLR because these are already correctly set up for us. We just had to change this single byte. It's a little bit different in our case because we need to change this nibble here, which in theory we know, but the issue is we don't know this nibble right here. But what we could do is we can only change it at byte granularity. What we can do is we can overwrite the last 2 bytes to be E613. The issue with that is that it's not always going to work. So if, let's say, we just overwrite the last 2 bytes to become E613, we just overwrite 2 bytes, make them E613. In this case, it would work, right? Because suddenly this whole address would just change by these 2 bytes. It would become E613. We know that's where the win function is. We would suddenly win. But that doesn't always work. So if we can imagine if we run it again and we look at it, if we had passed in to make the last 2 bytes E613, we would not have won right here, right? Because it actually doesn't, it shouldn't be E613 if we want to win. It needs to be 0613. So we were wrong here. But this is fine because this is we can do a brute force here. This value being correct will be correct 1 in 16 times. So if we just keep running it, how do I quickly do it? If I do echo 100 test, does that work? Yeah. So we can see here we would have won. We got our E613 we want. So actually, let's just do grep win auth. Address win auth. Address win auth. Okay. And maybe we do for I in seek 32, do that, done. So we can see if we run this a bunch of times. So here we would have lost, we would have lost, we would have lost. Lose, lose. Lose, 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 lose. And all of these would have lost. We're not lucky. Am I looking at the right byte? Yep. Here, though, we would have won. So if we had just decided to overwrite it with E613, in this run of it, we would have been correct. Hopefully that makes sense where this brute force is coming in. So we're not brute forcing all of ASLR, we're just brute forcing 1 nibble of ASLR. Because we know that maybe we'd have to experiment a bit more with this if we didn't know this exactly. We'd have to analyze the offsets, kind of how far away they are. You could imagine if we had a really large program where functions could be like several bytes away from each other, that you would, in theory, then have to brute force more, right? So for instance, if you're operating in the context of libc and you're trying to change, or you're like, hey, we're returning to this libc function, Now I want to return to this libc function. Libc is a large thing. We might actually have to brute force like 12 bits in that case, which actually we'll see in later modules. But in this case, it's a super small binary. We just have a 1 in 16. Even 12 isn't that bad, right? That would just be a 1 in 4096 if you can run it sufficiently fast. You can just brute force that. It's significantly better than having to brute force like, I don't know, 6 bytes or whatever this is, which is just non-tractable. Okay, hopefully that makes sense about this challenge. I'm trying to see if there's anything else that's maybe important to talk about with that. Yeah, so I think in past levels, I think whenever you overwrote this, I'm going to guess that we probably had PIE disabled, so you knew the full address to be overwriting. But the other thing I'm looking at here that's kind of tripping me up is that we have a canary. Oh, right. Okay, so maybe you've already done this in a past level, actually, what I'm talking about, but hopefully that helps for if you're on whatever that past level is. This level has a little bit more to it. So like some of the past levels, it'll tell us what we said, which is interesting. If we're going to include that functionality, there's probably a reason. You're probably going to be using it. And then it also has this other thing that it tells us at the end. As a trick hidden in its code, reverse engineering the binary right after this puts. So, I mean, we can do extremely basic reverse engineering. We run strings on this. And we will see that one of these here, this string is weird. It says repeat. We didn't ever see that in the output. So it turns out if we run the challenge, it's not super interesting. That's why I'm going to just quickly show it. And we send repeat. What it's going to do is it's going to call challenge again. So we basically just did a recursive call. So if you think about our stack frame, where should I show this? Think about a stack frame or our call frame. We had main that called challenge, and we called challenge again. Challenge just called itself, which is interesting. And then we also had that thing where it tells us to what just happened? Oh, send your payload, yeah. It also tells us what we said. So it says you said test. Okay. Did before it say you said repeat, I'd assume? Yeah, you said repeat. So we can think about similar to the previous level where we're talking about basically this idea of null byte terminated strings. Basically, you can use that concept to start leaking out data. And the thing that was tripping me up is that, hey, we have a canary in this level. So I think probably the previous level where you were brute forcing a nibble, the canary was turned off, but suddenly the canary is turned on. Now we need, in order to overwrite all the way through, because we're not like the previous level where we could just skip over the canary, we're forced to go through it, is important. We need to probably, unless we have some other clever solution, figure out what the canary is. And we have this leak primitive that allows us, if we can write right up to where the canary is, so let's actually just demonstrate that. If we, so we know that the canary is here. Input buffers here. Yeah, so this should be higher. If we look at this versus this, we will see that that is 40. Okay, so if we do 8 times 40, just so we can quickly copy it. If we do this right here, we say 100, we send our 40 A's. This isn't going to quite work, and we'll see why. Or maybe it will actually just work. Oh, the reason, yeah. What do I want to say about this? Yeah, so we can see that it says you said 40 A's, and then it's going to print out to us our new line character. And then it's also printing to us this garbage. So if we pipe this maybe through XXD, and we say 100, and then we send our 40 A's, it's going to say you said A, and then after these A's, so we can see here's our last A, and then we have our new line character, and then we have all of this stuff right here. That goes, I don't know exactly how far, I guess it would go 7 bytes, maybe further, maybe we're printing multiple things. It looks like we're printing more than just the canary, and we're kind of guesstimating that this is the canary, both because we computed the offset, so we know what it should continue printing for after those 40 A's in the new line is the canary. And then it would also be printing to us I guess it continues printing more stuff to us, so 7 bytes, so that would be 4. Here, 8, 6. I don't know. It's printing more stuff to us. I can't think right now. And this other stuff is probably going to be the saved base pointer. And then it'll eventually stop printing stuff to us. So I think we just leaked basically the base pointer, the saved base pointer, which basically tells us where the stack is located. And then we also leaked the canary to ourselves. Does that make sense? Is there anyone that's on this level thinking about it? Okay, so someone in chat says, so we have to first leak the canary, then do the filling to return the address. Yeah, so I guess that's the next important thing to think about, is that, and we'll get rid of this XXD stuff. If we do 100 and we send 40 A's, we saw that we're leaking out the canary and probably also the saved base pointer. But if we run it again, and this time instead of sending 40 A's, we do repeats, and then probably have to take some of these A's out to account for the fact that we increased on the length. So 1, 2, 3, 4, 5, 6. So subtract 6. 1, 2, 3, 4, 5, 6. Oh, we were sending a length. 100 repeats. 1, 2, 3, 4, 5, 6. We're going to see that what just happened here is it tells us you said repeat AAA, gives us the canary, but it didn't crash it. The program's still running. And the reason the program's still running is that the canary is not checked until the function returns. And we didn't return, we just called another function. We're not done executing this function. We just recursively called ourselves. So we're executing in the next stack frame. So we're executing right here. We're basically doing it all again, but this time we're doing it all again with knowledge of the canary. Now, of course, it's important to note that if we say, like, let's say our payload size is 100 and we just pass test, we're still crashing. The crashing is just delayed. So here we didn't actually do anything bad. We sent 100 bytes, test, whatever, right? This isn't a bad execution here, but this is going to return, and then it's going to return back to our function where we overwrote the canary, and then that's going to return, and that's where the stack smashing detected is going to happen. But we don't care about this. If we can win before this happens, we've won. It doesn't really, just doesn't matter. Hopefully that makes sense. What else? What else to note? Oh, I guess something that maybe isn't clear about this, and why I was initially confused. So I'm sending 41 characters instead of 40, which means I'm overwriting 1 byte of the canary, right? And that's important to keep track of. We just overwrote one of our bytes. But the very first, the least significant byte of the canary is always a null byte. And they do this as a protection mechanism. And it's actually kind of designed to prevent accidentally bugs that would leak the canary. So we can think of this, there's all of these leaking bugs that have to do with strings not being correctly null terminated, and they might just keep outputting data until it gets to a null byte. So the reason the canary always has the least significant byte being a null byte is so that if you fill up, let's say, a buffer that's 40 characters, you do 40 A's into that buffer, but you didn't null byte terminated it, even though it should have been, and then you print it, because just say you call puts on it. If this wasn't a null byte, you would leak the canary. But it is a null byte, which means puts would actually stop on this null byte. That's why this is always a null byte. But what we did, by accident, I guess, is we sent 40 A's and then a new line character, which means we sent 41 characters. Which means the reason, and that's why we're crashing, is we overwrote this particular byte, but that's the reason we can actually leak it out, is because we got rid of that null byte character, which allows us to keep reading more. And I think the other thing, I guess, that might be important to note is that every once in a while, I guess it's, I don't exactly, I have to think about what the odds are. These other bytes can also contain null bytes, just randomly. It doesn't prevent them from becoming null bytes. So you might have to run your script if you get unlucky a few times. It's pretty rare, I guess. Somewhere around 1 in 256. I don't know. I have to think about that. Yeah, so if we did randomly get a null byte character in the middle of our canary, we would not leak the whole thing. Okay. So the canary won't change the value when calling another challenge. Yeah, that's correct. So the way that canaries work, objdump-d and until challenge. If we look at challenge, so the canary gets set up right here. It's basically taking from this weird place, this segment register offset by hex 28, and it's moving that into RAX and then moving that onto the stack. So this value right here, which is where all functions are going to be pulling the canary from, this is initialized by the kernel. Well, is that true? I don't know exactly where it happens. The kernel definitely passes a random value to a process. It might be libc that decides to put that in this particular location. I'm not entirely sure about the origins. If we wanted to know more about that, there is the proc interface, proc self auxv xxd. So one of the things about when a process gets initialized is that there's multiple things, right? We know about argc, we know about argv, we know about envp. But it turns out there's this fourth thing. There's this auxv. And auxv contains auxiliary data, and somewhere in here, I believe, is the canary. Does this look canary-ish? Maybe it's here. Or maybe it contains a pointer to where the canary is going to be. I don't remember. I remember looking through this at one point. Either way, it's not super important. That would be a more very specific detail about how the canary works. I believe, though, that the kernel provides a process with some random data. And I guess it's storing a pointer to where that random data is. And then does libc put it into FS? Hold on. I'm curious real quick. We are not currently doing kernel exploitation. That will be in a couple of weeks, 3 weeks, I don't know, somewhere around there. This is buffer overflows, basically. Memory corruption. Okay, so I'm curious, just real quick. This. Here's how we could start figuring that out. So we need to grep to dump-d and until. So if we, oh no, we just copied the wrong thing. We don't want to obj dump the challenge. We want to obj dump libc. It might also be an LD. that this happens, and we grep for this. So this is going to be everything that has to do with this canary location. Guessing that this is just canary protection for all of this. Grep LEA. No. How would this show up? No. Let's just check. New LD. No. lib64. Maybe LD sets it up. Oh, yeah. 4304. 4304. So this crazy stuff, it's pulling this into RDX, pulling that, and at some point LD writes to here. We'd have to figure out exactly where this is coming from. This RTLD global read-only stuff. Yeah, we'd have to look a little bit deeper in, but it looks like LD is putting this into FS hex 28. But I believe that the kernel at some point initializes the process with some random bit of data that then LD can go on to use to become the canary. All right, that isn't super important to this challenge, but that's kind of how that works. And moral of the story, yes, the canary does not change when calling another challenge. Similarly, if you have multiple threads, the canary does not change. Oh, and also if you fork a process, the canary does not change either, which is an interesting security consequence, at least at some point on Android. I'm not sure if this has changed or if this is still the case. In Android, all processes basically fork off, I believe, of some zygote process thing. Android is based on Linux, and basically since it's constantly using fork, it's the canaries, at least at one point in time, all canaries basically for all of your processes were always the same. So if you could figure out how to create a process in Android and just make that process tell you what the canary is, now you just know the canary until the phone is rebooted, basically. I don't know if that's still the case, but that used to be an interesting consequence. And I think this idea will also be explored in another level of baby mem. I think the last level. Okay. Are there any final questions? Otherwise, I'm going to start wrapping up this office hours. It'd have to be a quick one, but I'd be happy to answer a quick question if there are any. I wanted to know some stuff about 13. All right, we'll take a quick look at 13. Any content you recommend for beginners? Depends what level a beginner is in your mind, I guess. Go through pwn.college, it's great. Okay. So you're saying mostly because we need to traverse backwards and I don't know how. Address we need to access with the flag data is before the input buffer. Is that true? Challenge function has just been launched. However, an important initialization step was missed. So I think you can see it here. I'm staring at this and staring at this for long enough. This data right here looks not like an address. It's probably not our canary. Our canary is going to be down here, but it does look canary-ish just because it's a bunch of random bytes. But more importantly than a canary, which can be random bytes of any value, it looks like random bytes of ASCII. It says where the flag is saved and the address is before the stack pointer. Okay, let's look at that. Okay. The canary. Input buffer starts here. Saved frame pointer, saved return address. The canary is stored here. Canary value. Where does it say? Where does it say that? Flag was. Can I just control F? Flag was. Oh, okay. The flag was read into this address. You're saying that it's before the stack pointer. 13E2. 13E2 is going to be somewhere around here. And where is our buffer? 13E2. Our buffer. So 13E2. E2, so approximately here, a little bit further in. And our input buffer is at 13C0, so it's going to be over here. But, so we're printing, maybe you're getting a little bit confused about how we're printing the stack. This is going to be further on, right? So if this is E2 and our input buffer is over here, so if we do 100 A, just so we can see some A's, and we can see AF2, AF2, so about here-ish. Where are our A's? We can see our A's are up here. Our A's are flowing downwards. They're flowing towards where this is. Yeah, sorry, that was a misunderstanding. I suppose it's just before input buffer. So it's not before, right? It's after. I guess maybe we're disagreeing on what before and after means, but these A's are flowing towards the flag. The flag is that 3B and on. AF2, so we're looking at AF2, and AF2 is going to be here, 2 bytes into this. So if we skip over this 3B and this 19, this is going to be the flag. So that means this is PWN.COLL. Yeah, we can see that's LL for sure, EGE. And then, yeah, the buffers, we can see our A's where our A's ended up going. So if we kept sending A's, we'd slowly overwrite the flag. And I'm guessing now that you see the direction of this data, probably the level makes sense. Okay. All right, I am going to end my office hours then. As always, if there's more questions, feel free to ask on the Discord. And yeah. All right, see you everyone.